let's go to resume our implementation. So as we have seen before, the transmitted signal that we have right now is not really correct, because for instance the constellation points doesn't have clear defined values, and we have many points here in between. So let's go to establish this correction, and let's go to first add some variables that we can use in our next block. One of them is going to be what we are going to call samples per symbol. We are going to set this into 4. We are going to also increment the number of samples that our random source is generating right now. And what we can also do right now is to add one block that we are going to call polyphase clock synchronization. So let's go into remove these connections that we have done right here. And in this moment, we are no longer interested to see the frequency and time response. Rather, that's just to make a comparison for the effect that we obtain by adding this new block that we call polyphase clock synchronization. And then here is going to add a new constellation, QT GUI, that we have exactly right here. And here in this block, we can read basically the documentation that we have about this building block. So this block has 32 built-in filters. Why? Because the error signal is the output of the differential filter. So basically what this block does is to compare filter by filter what is the one that provides us the minimum error signal in comparison to the input. And this is one of the reasons that we have here in the filter size this value of 32 and the initial phase of 16. And yeah, it's really a time synchronizer for PAM signals by minimizing the derivative of the filter signal, which in turn maximizes the S-on-air or software signal to noise ratio and minimizes the interference, inter-symbol interference. So let's go to really establish here what are the samples that per symbol. And in this case, what we are going to tell to this property is to put the symbols per second per samples per symbol that we have defined before. We are going to a little bit increase this value. Then we are going to set this loop bandwidth into 62.8 milli hertz, and then what we are going to do is to establish a new tabs. As I have mentioned before, the tabs is one of the parameters that we have to take under consideration to deal with the distortion that is generated for the multipath while during the transmission of data. And we require of a new variable that we are going to call, we are going to call this variable as RRC, that is going to represent the root raised cosine. And finally, what we can say is that we are going to send the 9 tabs. Later, we are going to add the value that this variable has. So at this moment, it's going to assign this value right here. And now what we have to do basically is to really calculate what is the RRC value. By default, there is a function that when we are going to use these finite impulse response filters, and one of them is this root raised sign. And as you can see right here, this filter has many attributes or many attributes or that we have to modify to make this calculation. And one of those values that we have are the number. Let's establish other variable here that we are going to say that we are going to call number of filters that we are going to set into the cherry 2. For this, we're going to make this closer to our block. And normally here we have the excess bandwidth, and instead of giving a numerical value, what we can do is to write this value as excess bandwidth into a variable. That is going to make easier its usage later on in case we want to modify them. So with this in mind, what we can do right now is basically calculate the value that we have to assign in order to calculate this filter, this root raised cosine pulse shaping filter. And to do this, what we are going to do is to invoke one function called first root raised cosine, and then we are going to do is to add the parameters that we have here, as you can see right here. So the first parameter that we are going to add is the number of fields. The second, we are going to repeat this because we have the same filters. We have to select between the bunch of filters that we currently have what is the one that provides to us the minimum error signal in the output. And then what we are going to do is to do one mathematical calculation, which we are going to write here. The symbols per sample. Basically, this is just the inverse of the symbols per sample. Here, what we are going to put is what is the aperture of this filter in frequency. And then finally going to do is to set the number of tabs, that in this case is going to be 11. We're going to multiply this value by the samples per symbol, and finally by the number of filters. And it is showing us here something in red, because is there something that we also have some typos errors here, and that is the reason why it says to us that this expression cannot be really evaluated. So let me check here what the problem could be, and then we can just continue with our implementation. As you can see here, I have a typo problem there, and that was the reason of our error. Now that these values are well written, then we can evaluate what is going to be the outcome of adding this polyphase close synchronization. So as you can see in the upper side, we have improved significantly the constellation diagram of our transmitter. However, it's not real perfect. And one of the things that we are going to do right now before continuing with this implementation is to really assign names to both constellation diagrams, because by doing so, what we are going to do is that the person watching this video is going to understand better how to positioning blocks into gaining radio. As we can see right here, there is one property called GUI hint, and basically the way that we can work with these properties is assigning the location with the first two coordinates. So basically what we have is the x coordinate and then the y coordinate. So basically what I'm telling in this moment is that I want the first graph, the graph without the polyphase clock synchronization in the left upper part of our GUI, and we are going to establish that the dimension of this graph is going to be 1, 1. Then in this case, what we are going to tell is that we want the second constellation diagram in the right upper part of our GUI, and it's going to also have a dimension of 1, 1. Here we can establish names. We can tell that we are going to call this constellation polyphase clock. We're going to do asset here, and in this case what we can call this graph is constellation channel model. Good. As you can see here, we have this GUI again. In this case, the channel model is in the upper part, on the constellation uh, after the polyphase clock filter is in the bottom. It's going to correct here some typos, mistakes that I made. And if we want to see one side by side to the other, basically we have to change here these coordinates. What we are going to say here is that it has to be in the x in 1, as it was the previous one, and in y also in 1. So as a consequence, now one is beside the other, and here we have a cleaner picture of our constellation diagrams. So far so good. So basically now what we are going to do is to improve this constellation diagram of our transmitter by using some equalizers. The equalizers, the basic function of those equalizers are to reverse the distortion when a signal is transmitted through a channel. And one of the building blocks that we have built in radio is what is called the constant modulus algorithm block. And let's go to look for this block right now. So equalizer, we can write right here. Here we find our equalizer block. And it's going to organize this thing a little bit better in order to make clear for everyone watching this tutorial what we are currently doing here. So it's going to just connect these building blocks, and then what we're going to see is what is the outcome that we obtain with all of them. So let's go to assign some parameters. As we have seen in the calculation of our root raised cosine filter, we have established that the number of taps is going to be 11. Then we have also established that the modulus is going to be 1. That's going to establish a really small gain, about 10 millis. And as we have already mentioned, if we are using QPSK, we have samples per symbol of 2. And what we are going to also do is to create another variable that we are going to call tabs. Tabs, and we are going to replace this into our channel model. And for this case, we can have two kind of these variables, or we can assign 2 different values to this variable. The first that we are going to assign is going to deactivate one of them, is 1 by default. And the second that we can do, that we can have, is that we can add the poles of the filter that these tabs uses to reduce the distortion caused by the multiband. So we can assign that the value that this tabs variable has is 1 and the other pole is going to be located in 0.25 minus 0.25 jot. The other one is going to be in 0.5, 0.5 J, and finally our last pole is going to be located in this in minus 0.3 plus 0.2j in the imaginary axis, and it's going to apply this, and then let's going to see what is the result that we obtain. As you can see right here, now it's real crystal clear, sorry, what are the position of each constellation point. Yeah, as you can see here we have 0.7 and here minus 0.7. So basically now it's crystal clear the improvement that we obtained by adding this this equalizer. Then what we are going to do is to add what is called the coastal loop. Basically, this is a recovery loop, as we are not using real devices, but rather we are using just here this example as a simulation. This simulation as example. What we are going to do is to make a synchronization of the QPSK symbols via this coastal loop. So let's going to look for the coastal loop, and let's going to unplug this thing here, and going to move a little bit to the right part. It's going to displace a little bit these blocks to come up with more space. And let's going to position them much better. So now what we have to do is to assign some order, and we know that the loop bandwidth is already here given. So it's going to repeat this value right here, and we have to also give an order. So this loop is going to have an order of 4. Why? Because we are using QPSK. If we use BPSK, we are going to use 2 and so on. Here, what we can do is to read a little bit more about what are the details about this coastal loop. As I already mentioned, it's a recovery model that logs to the center frequency of a signal and then converts it to the baseband. So basically, when we transmit our signal that is at the output of the CFA equalizer, then we transmit this into the medium. So basically, with the coastal loop, what we do is to put this radio frequency signal back again into the baseband. So let's going to connect those blocks, and let's going to see what we get right here. So in this moment, what we have to do is to check what is our outcome. As you can see here, it is crystal clear that what we are sending is basically what we receive, obviously, because it's a simulation. Let's go to add a new Qt constellation diagram to see this thing clearer. See Control V. Here, what we are going to do is first to deactivate this block right here, because we are no longer interested to see where is the outcome from the channel model, but what we are really interested to see is what are the constellation diagram of the transmitted signal and of the received signal. So we are going to call this constellation transmitted. And we are going to set this into the left part of our diagram. And we are going to call this constellation receiver. Or we are going to put this into the left part of our implementation. So here what we can see is the transmitted signal and the received signal, and what we can see is that it's crystal clear that what we are transmitting is what we receive after removing the radio frequency and signal. And now what we're going to do is to continue in the next block with the modulation to get our random source back, and this is what we're going to see in our next block.